In this video we're going to look at conjugate points on an ellipse which has been generated by an attractive force given by MUR. Now the equation we see here up at the top, we've derived that in a previous video, but what we do is we rewrite this equation in this form here. Now there's a derivation of this equation as well at the end of this video, so if you hang on you'll be able to see exactly where that comes from. So that's the equation there of the ellipse. So if we were to take that off, you can see that's the ellipse there. Now what we have here is that ellipse, and we also have a conjugate point. Now the conjugate point will follow that ellipse round as we move it, and there's a line here, the blue line there, which is a tangent to that conjugate point. Now we've also got another line here which is tangent to this point here, which is in blue. Now you'll note that both of these lines, they meet at a right angle, okay, and at that point where they meet at the right angle and the crossover, that will be a point on a circle, and that's called the director circle. So let's shift this along to a different point. Okay, so if we shift we shift it up round there, so let's move to that point there. Now what we can do is we can find this other point in the director circle by moving that little blue point, so the green line moves. Okay, so if I just shift this round to here, now it's a bit kind of minus 2.2, so it's minus 2.19, say it's roughly there, 2.18. So you can see that now we've moved this point round again, and we can note that at right angles there, both of these points meet. So when they cross there, both of the points meet again on this director circle. We could keep doing that. We can keep moving this ellipse round, and then we can keep positioning this other blue point, purple point, and it will meet on this director circle. Okay, so and it means that these 2 points here in that case will always be conjugate points. So let's have a wee look as well and see what happens whenever we turn this ellipse into our circle. So if I was to make this, I think we put it at 1.57. okay, now if I then adjust the angle, I don't want to do that really, do I? Just alpha. Okay, if I adjust alpha to 0, so now we've got a circle. Okay, now if I was to again move this round in order to get the crossover point, so if I shift that round to get that crossover point, so there we go, crossover point. You don't actually see it there, it disappears at that one, but you will probably see it up here, see it up just about there. Okay, so it's minus 3.1 over 3.14. Okay, now you can see that it doesn't quite cross because I actually moved the value of that slightly, so I'll just shift it back. I think it was 6.3 it was sitting at, so that's 6.3. Okay, so you can see that again is crossing at right angles, but the difference between this here and the previous one that we saw, which was a force of attraction given by an inverse square law, is that the conjugate point here now sits at 90 degrees. Okay, it doesn't sit diametrically opposite 180 degrees. The conjugate point now sits at 90 degrees. So let's turn this back into an ellipse and we'll finish this off. So we'll make this a value here, say 0.7. We'll adjust this round. Okay, so we can see that the conjugate point is now here, so it means that we can adjust this round here. Okay, we don't need to get it exact. Okay, so it sits somewhere here, and it's going to sit and it's going to cross over on the director circle. So this angle here is the angle between the two conjugate points. So say that's point A and that's point O, then that's point B. So if this angle AOB is going to be the angle that's the angle between both of these points here, which are the conjugate points. So if the angle theta is going to be less than that angle, then we're going to have an action which is going to give a weak minimum. But if it's greater than that value, then we're going to have a stationary value, but it's either going to be a minimum or a maximum. So we'll allude to that again at the end of this video. So I hope that's of use to you, and it kind of covers most of what's in the pages 53, 54 of the Charles Fox book. That's given a good graphical description of the conjugate points given the direct distance law. Now what we want to do is go ahead and prove those analytically. So we started off with this equation here. So again, we derived this in the previous course. Now what we want to do is we want to rewrite that in terms of r. So I've worked through this derivation here. So what we're going to do is replace the values of our c squared with this term here. So every time we see c squared, we just stick in the a squared upon 2 cos alpha. So we're going to have c squared in the top line, so it'll be a squared, and we've got our 2 cos alpha on the bottom. And we've also got our a to the 4 divided by 4 times. Now it's going to be c to the 4, which is equivalent to this squared. So it'll be a to the 4 upon 4 cos squared alpha. And that's all minus 1 to the power of a half times what we've got left over here. And also we've got our c squared replaced at the bottom line here for this one. So whenever we multiply these out, the left hand side stays the same. This whole thing here simplifies to cos alpha, and this here remains at cos 2 theta plus beta, and this whole bit here, the 2's cancel out, the a squareds cancel out, that goes to cos alpha, and then we multiply the right hand side here by the left hand side by this. So we in effect take this up here, and that just multiplies out, so we get our r squared, and we've got 2 cos squared alpha and our 2 theta plus beta, and that's the terms multiplied this one here as well. We can take out a common factor here of our r squared, and it's going to give us this value here, and we can rewrite this here by taking this term here down below. We've got this term down below here, and this term here, again using another trig identity, is going to give us this equation. So this equation here is the equation that we see actually in the Charles Fox book, which I believe is in page 53. If you go to the bottom of page 53, we've got this equation here, and what we'll do is we'll just rewrite it in this term here. So we'll just take the square root, and we'll work with this equation here, and we're going to use this equation in order to work out an analytic derivation of the x coordinates of the conjugate point. So let's go ahead and we'll do that now. So I've rewritten the equation here which we're going to differentiate. We can see here that we've got our dependent variable r, the independent variable is the angle theta, and our 2 constants here are our alpha and our beta. So we're differentiating with respect to these constants. So we're looking for partial r by partial alpha, and we're looking for partial r by partial beta, and then we're going to have to divide both of them out. So we'll first of all look at partial r by partial alpha. So we're differentiating this thing here with respect to alpha. So we're going to have a function here within the bracket. So it's going to be minus a half of a times, well, we leave what's inside the brackets here. So we'll leave that inside the brackets, and then we take away the power of 1, so it will be to the minus 3 upon 2, and then we differentiate what's inside the brackets here with respect to alpha. So with respect to alpha, we're going to have this here is going to be differentiated with respect to alpha, so the cos 2 theta plus beta will just remain the same. So this is this cos 2 theta plus beta, it remains the same, and we differentiate the sin 2 alpha, and that's going to give us the 2 cos 2 alpha. So that's the first bit here done. The 1 disappears when we differentiate. We've got to differentiate this here with respect to alpha again. That's going to give us our 2 sin 2 alpha. So we're going to get this here for the full differentiation. And then what we can do is we can rewrite this here, and we can cancel out the 2's here, and we can take the value minus 3 upon 2 underneath the line here, and it becomes the power of 3 upon 2. So this is our differentiation here. So we'll leave this one here for the moment. So this is our partial r by partial alpha. We'll then go on and we'll look at partial r by partial beta. So we're differentiating this thing here with respect to beta, and it's the same process again. We're going to have a half of a, so a half minus a half of a, sorry, times the what's already inside the brackets, so that remains inside the brackets, to the power of minus 3 upon 2, and then we've got to differentiate this here with respect to the value of beta. Now this is not a function of beta, so that disappears. Again, 1's not a function of beta, it disappears. So we're just differentiating this here with respect to beta. So this part here, sine 2 alpha, it just remains exactly the same as it is. So we come down here, we're going to have our sine 2 alpha here, and we're going to differentiate this here, cos 2 theta plus beta with respect to beta. So it's going to give us the 2 will come out, and we'll go, the cos will become a sine. So it'll be 2 sine theta plus beta, and we can see that's what we've got here. We've got our, we'll be left with our sine 2 theta plus beta, and another factor of 2 will have come out, and that's that factor of 2 here. So this has done the differentiation here with respect to beta. Again, we can rewrite this by taking the minus 3 upon 2 underneath the line. It becomes to the power of 3 upon 2. Now, these are our two equations here, our partial r by partial alpha and our partial r by partial beta. Now we have to divide this equation here with this equation here. So that's quite straightforward. When we divide throughout, we've got to multiply by this reciprocal. So in the end, we're going to have this line here is exactly the same as this line here. So this line and this line are going to cancel out. So what we're going to be left with is the top line from this equation, which is this line here, and also the top line from this equation, which is this equation here. So we've got this one and this one. And then what we can do is we can rewrite this, and we can, the minus and minus will cancel, and we're going to have the equality. So we're going to make it equal to the same value here, but without the theta. So it's theta equals 0. So on the right hand side here, we've got our theta equals 0. Okay, and you can see that the sine 2 alpha is going to disappear as well, because the sine 2 alpha would be in the bottom of this line and also in the bottom of this line. So it means that both of them can get cancelled out. So these are our two final equations here, and I think if you look in the Fox book, page 54, you'll see that this is the equation that he derives on page 54. So finally we can say that if the angle AOB is less than the angle theta, so we get the angle theta from here, so we're going to solve this here for theta, then we can say that the action is going to be an extremum, so we're actually going to get a value for a minimum or a maximum. Now, if that's not the case, then we're going to get a stationary point, but it's not going to be a minimum or a maximum. Now, we've seen that whenever we looked at the actual video on the graphical calculator, and I think you probably learn more from the graphical calculator and the geometric ideas rather than from the mathematics here. But it does make it solidify it, and it covers the mathematics as we have done in the previous videos for previous examples. So that's all for this video. Thank you for listening. I'll get you on the next video, and also if you get any problems with the derivations, just get in contact with me. Okay, goodbye.